Hey, so welcome back, and this is another daily LeetCode problem. So today it was yet again another dynamic programming slash greedy algorithm, and it's called reducing dishes. So what it is a hard level question, and you're given a list of dishes with their associated satisfaction levels. And so the higher the value means kind of the customer liked that recipe or dish more. And so a negative value naturally isn't very good. So you want to avoid the negative ones. And so you want the highest value. It's a maximization problem. And so what you want is the maximum sum of the like time coefficient. And so in this case, the like time coefficient is just the index multiplied by the satisfaction ratio. And so in this case, the index here you say is 1, so it's a 1 based index. So it'd be 1, 2, 3, 4, 5. And so say you're trying to find the like time coefficient of just one of these values, like this one, it would be -8 times 2, okay? But you want to maximize the like time coefficient. And so two ways you can do that is one of them is you can actually sort these. And so naturally, as the index goes up, you want to be having increasing kind of satisfaction levels with them. And so because the 1 index is here, so it goes like 1, 2, 3, 4, then 5. And so the way you would want to sort these is you would assume is that, okay, I would want to make it in increasing order so that, say, 5, which is the largest number, goes here, and -9, which is the smallest number, goes here, and there would be like -8, and then say -1, and then 0 here. Okay, so that's one way that you can maximize this like time coefficient. And then the second way is you're actually allowed to discard or to remove some dishes. So in the case where, okay, do we really want -9 times 1 here to be added to our maximization result, our maximum sum of our like time coefficient? Probably not, so you'd scrap that. And so -8, do we really want that in our max result? Probably not, because -8 times 1, because this would be reduced down to 1 because this no longer exists, is probably not, because that would subtract 8 from our max result, so you'd scrap that as well. Now, the trade-off with this is as you're removing numbers, the corresponding index of these larger numbers decreases. And that's bad because before, what we were doing was 5 times 5, which is 25. And that's because before there was 5 numbers here, so we could really, enlarge and enrich that last number to get 25. And so, but as you're reducing the number of numbers, this coefficient that we're multiplying against our largest number decreases. So now, because it's going 1, 2, then 3, since all that we have left, if I clear this, is since we got rid of -9 and -8, all we have is -1, 0, then 5, which therefore have the indexes of 1, 2, and 3. And so then you would get a sum of 14, which is the result for this. But you can understand, hopefully, the trade-off that you're making is by getting rid of these two numbers, you're no longer multiplying 5 by 5, which results in 25, and 0 times 4 in the case, which is still 0. And then this would have been -1 times 2 or 3, which would have been -3, and so forth. So you're losing out on the larger numbers by reducing the number of values that you're including. And so the reason why we kept that -1 there in that case is because, well, we have -1, and then we had 0, which is at index 2, and then we have 5, which is at index 3 then, is okay, say if we got rid of this value -1, before we have the total sum of 14, which is 5 times 3 minus 1, is then if we get rid of this number, then this is now at the index of 1, and this is at the index of 2, and so then you'd only get 10. And so in some cases, you do actually want to keep the negative numbers. You don't always, it's not as simple as, okay, give me all the maximums, sort it, and get rid of the negatives. There's a bit more intelligence behind it, and that's what makes it a hard question. Okay, but we should kind of keep that in mind of, okay, I still want to sort this. And so we'll take our array. I'm just going to make it simpler for me and just call this array. And we want to sort it still in the same order so that it kind of goes in increasing order. So as you go far, you get larger numbers, right? And as you go to the start of the array, you're going to get, if you're going from right to left, you'll get more and more kind of negative increasing or decreasing, I guess, numbers. And so what you want to do here is then say, okay, well, I want a result. So we need some value that we want to return, and it's initially 0. And so we want to iterate through this array that we're given. And so after we sort it, we're going to see that it's like, okay, it's once again, -9, -8, -1, 0, then 5. Okay, and so I'm going to give it the corresponding indexes. So this is 2, 3, 4, then 5. And you can just ignore those periods there. And so we're going to iterate through this actually backwards in this direction. Great. And so with that, you're going to say, okay, 5 times 5, which is 25, and so forth. That's kind of what we did before, but we're actually going to ignore these indexes actually. Okay, and so, great, I want to modify this. So we're actually going to ignore these, just like that. And so what you're instead going to do is say, okay, as we're iterating backwards, I want to just keep adding the running sum. And so what that's going to look like is we're going to visit this value, and this will kind of represent our sum here, our sum. And initially it's going to be 5. And then we're going to also have a result. And so we're going to add to our sum and then also add to our result that sum. And so we've now added 5. And then when we get to 0, we're going to add +0 to our running sum, which is still 5. And then we're going to add that running sum to our result, which is now 10. And then when we visit -1 here, you're going to see that we add -1, which is 4, because 5 minus 1 is 4. And then we're going to add that sum to our result, which is now 14. And hopefully you kind of see that, okay, this is actually our answer. But as we go down, say we've already added -1, and so then we want to add -8. So we do 4 minus 8, and this is -4 now. And so what you should assume or think is that, okay, now I'm starting to add increasingly negative numbers. Like it's only going to get worse because we know we've sorted it. So as we go further to the beginning of the array, it's going to increasingly worse. So once we see that we're only adding negative numbers here, let's just stop there and return that result because we know it's only going to get worse. And so this is how you find that trade-off with the ever-increasing indices, like 1, 2, 3, 4, 5, is although we're not multiplying this value 5 times 5 to get what you'd expect is like the total kind of lifetime coefficient, you're instead implicitly doing that multiplication because the multiplication is just kind of adding multiple times. Like 5 times 5 is just adding 5 times. And so what you're just doing is you're adding plus 5 here, plus 5, but really now it's like +5 minus 1, and it's like +5 minus 1 minus 8. And so it's a way so that you're still able to get that multiplication from, okay, this is what the lifetime coefficient would be for a particular index, but you're kind of doing that in a lazy way by just doing the addition each iteration rather than just simply multiplying the index straight out the gate by 5 times 5 and 0 times 4 and -1 times 3. So hopefully that makes a little bit more sense. Maybe rewatch the video or watch a different tutorial if it didn't make much sense. But I found for me, looking at the code really helped make this explanation make more sense. So I'll write out the code, explain along the way, and maybe then it'll click for you. So yeah, so let's do it. So what we're gonna do is to implement that algorithm is we're expecting to return this result at the end. But once again, like I just described, we're gonna need to keep track of like a running sum. And I like to think of it as a snowball. So I'm gonna actually write it out as a snowball, because as you're going backwards, it's kind of like if you rolled a snowball down a hill, it gets bigger and bigger and bigger. So as we iterate backwards, this running sum gets larger. So actually, I'll just call it running sum because that probably makes more sense for you. And so while this array still exists and our array at -1, so -1 is going to be the last value in the array, and plus our running sum is greater than 0. And so the reason why we're actually checking the last value in the array and checking if the array still exists is, maybe you've guessed it so far, is we're actually going to be popping things off from our array. And this makes it easy when you're grabbing values from an array, because you can just keep grabbing the last value that you just looked at. It's just a simple way of working with things backwards. And so what you're going to do is you're going to say, okay, our current running sum is going to be equal to itself plus the last value in the array. And we're just going to pop it off the stack because we're not going to have to ever think about that value any longer. And so from there, with that running sum is each iteration, we're just going to add that running sum to our result. And that's literally the algorithm. So to add a bit more details to it, so it's very simple because we're once again just, as we're moving backwards, we're just aggregating values that we've seen previously. And so then we add 5, then we add 5 plus 0, then we add 5 plus 0 plus -1. And so that value keeps getting updated in the running sum, which then correlates to being added to the result. And so we only stop once that running sum that we've been kind of aggregating in our snowball backwards starts getting below a positive 0 or like a greater than 0 function. Once our running sum becomes negative, there's no reason why we want to keep adding it, because we're trying to maximize the like time coefficient. All right, and so for time and space complexity for this, for space complexity, it's just O of 1 because we're simply using the array that's provided to us. However, the time complexity is n log n, and that's because the bottleneck here is sorting the array. And so it's a good thing to keep in mind that once you sort, the best that you can do is n log n time complexity. And so, or that can be the bottleneck. So because this is just an O of n loop here, since we're just iterating through each value and popping it off from array once, and popping is O of 1 time, then since this is O of n and this is n log n, this is the bottleneck for time complexity. Okay, so it's n log n time and O1 space complexity. So yeah, I hope that helped. It's relatively little amount of code for a hard problem. It's more just coming up with the problem intuitively during an interview or in a competition. That's the hard part. So yeah, I think taking it step by step, sorting it, looking at it, okay, how would I do this forwards? How would I do this kind of backwards? And just looking at it at all angles. I think it's relatively fair of a question, but I understand why it's hard. And I didn't get this myself today. I had to look it up. But yeah, explain it to you all. Helped me. So yeah, I hope it helped you as well. So have a great day and good luck with the rest of your algorithms. See ya.